repeat a bit of that. All right, so in section 4.4, the last section in chapter 4, we're going to look at permutations, which are groupings of things where order matters. And we're going to look at combinations, which is groupings of things where order does not matter. And that's going to be the first question that we ask ourselves when we see a problem. So one of the first things we're going to do when we look at any problem in this section is we're going to ask, okay, does order matter here or does it not? And then that will tell us whether we're dealing with permutations or combinations. Now, one key to both of these is we can't have repetitions. So there's no repetitions here. And that'll be clear when we do some problems what I mean by repetitions. Yeah, in both. No repetitions. So there's going to be we're going to have unique solutions for that case where we do have repeated things. What do I mean by repeated things? So if I'm making change for $1, right? Well, I could give you 4 quarters. Well, I'm not going to look at those quarters as quarter 1, quarter 2. They're all the same, right? They're interchangeable. That would be a repetition. I have 4 things that are exactly the same. Okay, now permutations is this. It's NPR, where N is your total number of things. And that's been the definition of N throughout this course. And now R is the size of your groupings. So let's say there's 20 students in this class, N would be 20. And then I want to form you into groups of 4. Then R would be 4. Well, we'll find out that there's many, many ways I can do that. If I take 20 people and I want to group you into groups of 4, there's that would be a case of combinations that I can make that happen. And this definition of N and this definition of R apply to both of these things. So they don't change depending on which case we're in. Now, for permutations, it's NPR, and that's a button on your calculator, by the way. So you don't want to do this by hand, although we can do it by hand. The formula by hand is N factorial divided by N minus R factorial. And this now begs the question, well, what is a factorial? So an exclamation point is what we call a factorial. This is also a button on your calculator. Well, let's do an example. It just means, let's say we have 5 factorial. This means you take 5 times 4 times 3 times 2 times 1. So you take whatever number you have and then you do successive multiplications from that number all the way down to 1. And if you did this, and 5 factorial would be 120 in this case. Again, it's a button on your calculator, or you can do it by hand if you choose. Okay, combinations then, the button on your calculator is NCR, and it's N factorial all over N minus R factorial. Notice it's exactly the same as NPR, but then there's one more term on the denominator, that's R factorial. So notice, it's exactly the same except for this extra R factorial in the denominator. Therefore, if I have an extra term in the denominator, that will make this answer smaller than this answer. So you can get fewer combinations than permutations, and here's why. Let's say I make you into a group of 4. The combination says your 4 names, I don't care how I write those 4 names. Okay, you're one group. Permutation says I do care how I write your names. So there'd be one grouping where your 4 names are in alphabetical order, another grouping where your names are in reverse alphabetical order, and then another grouping where your names are totally jumbled up. So permutations you can get a lot more groupings out of. Okay, and then on your calculator, what you want to look for, and this is a good time to remind you that on the test you cannot use your phone calculator. You'll need to use a I have like a $12 solar panel calculator for this course. It's very simple. And under that calculator, you're going to look for, there'll either be a probability button. It'll literally say like probability, PRB, or it might say stat. And then underneath these buttons, whichever one you have on your calculator, it'll say, there'll be one that says NPR. And then there'll be one that says NCR. And there'll be an exclamation point that stands for factorial. So you have access to all these on your calculator. And I should also mention, I don't even think that the phone calculators have that. So another case for you probably want to invest in like a $10, $12 scientific calculator. Okay, so that's basically the theory we need for most of today's problems. Let's look at 31. In horse racing, a trifecta is a bet that the first three finishers in a race are selected, and they are selected in the correct order. Does a trifecta involve combinations or permutations? So the second they say that order, correct order, that means order matters. And in order matters, that's a permutation. So again, the first question we're often going to ask is, do we care about order here? So the best answer, so anyone that says combinations is out. Because the order of the first three finishers does make a difference, the trifecta involves permutations. That's correct. Which is also why if you bet trifectas at the sports betting arena, you can get really good odds and make a lot of money if your horses come in that order. Okay, 32. Low probability that you'll win though. Okay, 32, a combination lock uses three numbers between 1 and 97 with repetition. Notice when it says with repetition, all that stuff I just talked about, combinations, permutations, are both out the window. So combinations, combos, and permutations are out because it says with repetition. And I specifically said that those formulas cannot handle repetition. So this is a different one entirely. And they must be selected in the correct sequence. Is the name of combination lock appropriate? Why or why not? Well, we could answer this right now. Is combination lock appropriate? Well, we just said combinations is out. So no, it's not appropriate. So this yes is out. B is out. And I'll just give you this one. So this one relies on what we call the fundamental counting rule. And the fundamental counting rule says this. I like to call it choices. Not just me, that's often how it's referred to in math circles, is choices. So in this one, choices is this. The number of possibilities is equal to the number of choices you have for selection 1 times the number of choices for your second selection times the number of choices for your third selection times ... the number of choices for your last selection. So this was A is the answer to this one. So the number of possibilities for this lock would be this. I look at the number of choices I have for my first digit in my lock. Then I multiply that by the number of digits for my second position in the lock. Then I multiply that times the number of choices I have for the third position in the lock. Now, if there's between 1 and 97 numbers, my first digit could be between 1 and 97. That's 97 choices. See how this works? Now, because repetition is allowed, the number of choices of digit I have for my second number are also 97. And then the third possibility for my lock is, again, I have 97 choices. And you just pick one. So I'm picking 1 out of 97 here, 1 out of 97 here, 1 out of 97 here. But you multiply those together, it'd be 97 to the third. And you don't need this number, but why not just write it so you can see there are almost 1 million different combinations to this lock. 912,000. So this is why you can see that most locks don't need to be overly complicated, right? Like if you have a safe, typically you rotate to the right to one number between 1 and 100, or 1 and 99, and then left for another number between 1 and 99, then right again. That's 99 times 99 times 99. That's over 1 million different combinations that it could have. Okay. So this is choices. This is another important one that we'll look at. This is also why places like pizza restaurants on their commercials can say, we have over 1 million combinations of menu items. Because of this. You have 12 different toppings, times 3 different crust types, times 15 different desserts they offer, times 12 different sides, times 10 different drinks. And you just multiply those numbers together, and yeah, then they can quickly get over 1 million and say, yeah, we offer a huge combination of different things. Okay, 33. A social security number consists of 9 digits in a particular order, and repetition of digits is allowed. So again, repetition is allowed, so our permutations and our combinations are out. Not going to look at those. After seeing the last 4 digits printed on a receipt, if you randomly select the other digits, what is the probability of getting the correct social security number of the person who was given the receipt? So this is, again, choices. And a social security number has 9 digits. So we have 9 choices here. 9. So N1, N2, N3, 5, and 6, 7, and 8, and 9. But it says the last 4 have already been determined for us. So we know the last 4 digits. So those are no longer choices we can make. So they're out. So we have to try to guess the first 5 digits. And now here's where you have to just be careful. How many digit choices do I have for each number? Well, it consists of Social Security. Okay, so 9 digits. So there's 9 total numbers. So don't confuse that. Each of these numbers has a choice between 0 and 9. That's actually 10 possibilities per number, right? So I can have 0 to 1 to 2 to 3 all the way to 9. So, and because repetition is allowed, I have 10 choices for the first number, 10 for the second, 10 for the third, 10 for the fourth, 10 for the fifth. Now, if I had all 9 possibilities, that's 10 to the 9th. Let's think about that for a real quick second. If Social Security numbers are only 9 numbers long, and each digit has 10 options, that's 10 to the 9th possibilities. That's 1 billion people. So now you have to ask yourself, will we ever have to add more digits to Social Security numbers in this country? There's 330 million of us, but keep in mind, I don't think that when people die, they recycle those numbers, right? I don't think they do. So that means there can only be a total of 1 billion Americans that ever live before we have to start either A, recycling Social Security numbers, or add a 10th digit, which would then give us 10 billion possibilities. Does this make sense? These are the things you have to think about. In fact, we'll do an example where we talk about phone numbers, where we had to add more digits to phone numbers because we ran out of numbers. Okay, but in this one, because the last 4 are out, we have 10 to the 5th here, which is 100,000 different combinations I'd have to try to get this person's Social Security number correctly. Now, be careful. The last step is convert this to a probability. So a probability is there's 1 correct ordering for that Social Security number. So that person has only one Social Security number that's right out of 100,000 possibilities. So the probability is actually 1 over 100,000. Okay, 34. A presidential candidate plans to begin her campaign by visiting the capitals in 3 of 49 states. What is the probability that she selects the route of 3 specific capitals? So she's selecting 3 specific capitals. So notice order matters. Does it make sense to have repetition here? Like, is she going to go to Des Moines and then go to California and then come back to Des Moines? Would she visit a state twice? Probably not. The whole point is to try to get to as many as you can so you don't repeat. So this is no repetitions. Because it's no repetitions, we should think permutations or combinations. Now, we just agreed that order matters, so certainly the people driving her campaign staff, they're going to care, you know, hey, what states are we going to, so they can plan it out. So order definitely matters. If order matters, then that's going to indicate permutations. So we are looking for the number of permutations. In the permutation formula, I just need to know 2 things. What's the total number of things that we're looking at, and what's the size of the groupings? Now, it's almost always the case that, well, it will always be the case, n is the bigger number. So it makes it easy to figure out if n is the bigger number, and I only have 2 numbers, then n is 49, which makes r 3 in this case. So she wants to take all 49 states and then put them into groupings of 3, and then decide which grouping of 3 she will actually perform. So on your calculator, you could do it this way. You would type 49, then you would type the NPR button. You would find that key on your calculator, and you would hit that. Then you would type 3, and then you would type enter, and it will spit this out. There are 110,544 different permutations of 49 things into groupings of 3. So there's a lot there. Now, here's how you would do it by hand. 49 NPR 3 is equal to, the general formula is n factorial over n minus r factorial. N is 49, so 49 factorial, all over 49 minus 3 factorial. (49 minus 3 is 46 factorial. So just subtract these two, you get 46, and then apply the factorial symbol. 49 factorial, I'm going to start to write it. It is 49 times 48 times 47 times 46 times 45 times 44 times 43 times 42 times 40, all the way down to 1. Or at any point you can stop and say times 46 factorial. Because every number after this would just be 46 factorial. And now you can say this. 46 factorial on the bottom cancels with 46 factorial on the top. And this whole thing simplifies to 49 times 48 times 47. And if you do that on your calculator, you will get the exact same answer, 110,544. Now again, to turn this into a probability, it would be there's only one grouping that she's going to pick divided by this number. So a probability for these problems is always just there's one solution out of 10,000 possible combinations or permutations. Okay, 35. A moving company has a truck filled for deliveries to 4 different sites. If the order of the deliveries is randomly selected, what is the probability that it is the shortest route? So first off, notice the shortest route, there can only be one of these. Now notice in this problem, they don't give you two numbers. Two numbers is almost a dead giveaway that you're going to use permutations or combinations. So I don't have two numbers. So this one turns out to be another example of choices. But in this one, it's kind of a modified choices, and you'll understand why in a second. The first choices we saw had repetitions, right? So I can have the same digits in my social security number. I can have the same digits in my lock. In this one, does it make sense to repeat a delivery site? So it doesn't make sense for me to go to an apartment complex, deliver something, go make other deliveries, and then come back to that same place. That would be foolish, especially since my truck's going to have all of the items I need as soon as I leave the factory. I'm not going to make multiple stops. So because of that, our choices get a little different as we go along. So let's just logic this one out. So the number of possibilities is equal to, well, I've got a choice for my first stop times a choice for my second stop times a choice for my third times a choice for my fourth. I'm making 4 stops. My first choice, I have 4 options because there's 4 different places we can stop. But then I'm going to pick one of those and then I'm going to throw that one away, right? Because I'm going to go there, which leaves how many options for my second stop? 3. That's the logic we need. And then I'm going to pick one of those for my second stop and throw that one out of the runnings. And now for my third stop, I only have 2 choices. And then once I pick one of those 2, I only have 1 left for my fourth stop. So this is actually just 4 factorial, because in this case, my where we have no repetition, in this case, we just use n factorial. So the number of choices we have, factorial. So in this case, it's 4. And if you do this, 4 times 3 times 2 times 1, it's 24 possibilities. Now again, the shortest route, there's only one of those. So the probability of randomly selecting the shortest route, there's one of those out of 24 possible routes. So it's 1 over 24. Any questions on these so far? So the challenge of this section is I've shown you what, like 4 different scenarios already. And the challenge is picking the right one when I'm not here guiding you. It can be a little tricky. But the more practice we get, the more hopefully it sinks in. Okay, 36 is yet another new one. So this is our 5th strategy. And this is one where we have repetition is allowed, but we're also looking for combinations. So it's a different one even than the other ones I showed you. So a classic counting problem is to determine the number of different ways that the letters of personnel can be arranged. Find that number. So the number of different ways we can arrange letters. So in this one, so this is a repetition allowed, repetition where order matters. So order matters makes us think of permutations, but in permutations you can't have repetition. So in this one we have a new formula. So the number of permutations is equal to n factorial, which would be the formula where I'm picking things, but as I pick them, I remove them from the running, divided by n1 factorial, n2 factorial, ... nk factorial. And let me describe what each of these is. So in this type of problem, n is the total number of letters. So for this problem, personnel, 1, 2, 3, 4, 5, 6, 7, 8, 9, n is 9. N1 is the number of first letter. So in this problem, our N1 is the number of P's. It's the first letter, and in this case it would be 1, because there's only one P in this word. Okay, N2 would be the number of second letter. So N2 for this problem would be the number of E's, and we have 1, 2. So there's 2 of those. And then generally in the formula, NK would be the number of the kth letter, or the last letter. So that's the form. Hopefully you see the pattern here. So N3 in this problem would be the number of the third letters. The third letter is R, so it's the number of R's. We have 1 again. N4 would be the number of S's. In this word we have 1. N5 would be the number of O's, and we have 1. N6 is the number of N's. There's 2. E's we already counted, so don't count that one again. And then our last one would be N7, the number of L's. There's 1. So for our problem, it's 9 factorial divided by each of these numbers with a factorial next to it. So it'd be 1 factorial, 2 factorial, 1 factorial, 1 factorial, 1 factorial, 2 factorial, and 1 factorial. 1 factorial is just 1. So all these 1 factorials we don't even care about because they're just going to be 1 times 1 times 1 times 1. 1 times any number doesn't change it. 2 factorial, these are each just 2's. So all you're getting out of this whole thing is 2 times a bunch of 1's, which is just 4. This gets a little more interesting when you have a word like Mississippi, where you might have 4 of the same of a letter, right? Because 4 factorial is actually a big number. 2 factorial, 1 factorial, these are almost inconsequential. And then if you type 9 factorial in your calculator, you'll get 362,880. And then divide that by 4. And that's going to give you, there are 90,720 different ways you can arrange the letters in the word personnel and make new words. So from the letters in the word personnel, you could get 90,000 other words. Now, granted, most of those are going to be gibberish, just letters rearranged in different ways. Okay, so maybe I can box this too, because this is another way now to calculate things. Order matters with repetition in this case. All right, let's look at 37. When 2 basketball players are about to have a free throw competition, they often draw names out of a hat to randomly select the order in which they shoot. What is the probability that they shoot free throws in alphabetical order? So again, alphabetical order, there's only one of these. Just like the shortest route, there's only one of those. Assume each player has a different name. So they're asking, what's the probability that they shoot free throws in alphabetical order? Well, first off, we can immediately write the probability is 1 divided by something, because there's only one alphabetical order. And then now we just need to know the number of possibilities. Now this problem is pretty simple. If I only have 2 basketball players involved, right, my choices become this. So my first times my second. For the first basketball player, my choices are between 2 people. So I have 2 choices. But now this is like before where we don't allow repetition, so no repetition. So for my second choice of who's going to shoot the free throws, I have to throw out whoever I picked after this choice, so now I'm down to 1 choice. So in this one, there's just 2 possibilities. And so it's just 1 over 2. So it's a coin flip, 50-50 shot that player A shoots first or player B shoots first. Okay, 38. How many ways can you make change for a quarter? Different arrangements of the same coins are not counted separately. So this is kind of how one of the examples I used at the beginning of class for making change for $1. If I have 4 quarters to make change for $1, I don't care about calling it quarter A or quarter B or quarter C or quarter D. I just say I have 4 quarters. Same thing here. So if we're making change for a quarter, I can use pennies, nickels, or dimes, but I'm not going to get into some game where I try to count, right? So I'm not going to care about having 2 dimes and 1 nickel and then calling, those 2 dimes dime A or dime B. Does this make sense? So you're not going to, don't overly complicate this. If you do, it can become very difficult to calculate. Unfortunately, this one is one where there's not necessarily a formula. Well, there is kind of a formula. Yeah, let's try to do this one with. So this is a combination. And we're going to, this one's a little tricky. So we're going to make this one into choices. So I have a choice for my first currency, a choice for my second, and a choice for my third. So if I have 3 currencies, pennies, nickels, and dimes, my first choice would be I have 3 options. So I could use all pennies, all nickels, or all dimes, right? And then I pick one. I say, okay, I'm gonna use pennies for my first currency. Now my choices for my second one are there's 2. So I'm either going to pick between nickels and dimes. Then I pick one. Now for my third, I have 1 choice. If you multiply these together, you get 6. But here's why this problem's a little tricky. Is that we could also reverse this. So if I picked pennies and nickels and dimes, there's another situation where I could have reversed that order and done dimes, nickels, and pennies. So then we're going to multiply this by 2, which is, we're going to say, we could also reverse this. So there's actually 12 different ways we can make this change. I've also shown this where, and maybe I'll show it here so it's easier to see. You can start with a table. So you can say, I'm going to do pennies, and then pennies and nickels, and then pennies and dimes, and then pennies and nickels and dimes, and then just nickels, and then nickels and dimes, and then nickels and pennies, and then What am I missing here? Oh, I kind of screwed this up a little bit. Yeah, I shouldn't have done, which one shouldn't I have done? The nickels and pennies. Because what you want to do here is then do a one where it's reversed. So this would be nickels and pennies. This would be dimes and pennies. This would be dimes and nickels and pennies. Nickels you can't reverse. This would be dimes and nickels. 6, 7, 8, 9, 10. And then I'm missing oh, then there's also one where you can switch the order on this and call it pennies, dimes, and nickels. So I just switch these two. And then there's one where I can have nickels go first, nickels and dimes and pennies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the 12. So nickels and pennies and dimes. Nickels, pennies, and dimes. That's true, but I think we wrote one of them three times. Or I think we wrote one of them twice because this would be 13 answers. Either way, you can kind of come up with this table, or you can come up with this combination theory here. And you also have to be careful, like you can't have just dimes, right? Because that will never add up to 25. Okay, 39. It says we've got, for a sequence of events in which the first event can occur n1 ways, the second n2 ways, the third event n3, and so on, where you take the number of choices times each option you have. This is called, we called that the multiplication counting rule. And I also called it choices. Okay. Then the last problem in this section, in this chapter, for the first half of the course, that's testable. We have, which of the following is not a requirement of combinations rule? For items that are all different, order is not taken into account. That's true. That R of the n items are selected. That's true, without replacement. That there be n different items available. That's true. So it's got to be B. What does B say? Order is taken into account. So we don't take order into account for combinations. And that will complete chapter 4.